All right, ladies and gentlemen, today we're going to continue with exponential functions. I know this is a lot of information. What I want you to do, though, is I want you to for sure get this definition here of the growth factor. It's 1 plus the percent rate of change. And also part of this exponential growth can be modeled where A is greater than 1 A is greater than 0 and B is greater than 1. This is where growth factor comes into play. You may also want to draw this model where we're talking about A being the y-intercept, B, or the base here, is greater than 1. This is considered a growth factor. And then, of course, our exponent. So here, this is stuff I want you to get written down so that you have it as notes. We're also going to do the same thing with decay on the next slide. So you might want to pause this video, get it written down, and then we'll move on from here. All right, we're going to talk about decay. So I do want you to write down this factor. It's 1 minus the percent rate of change. So A is still going to be greater than 0 because that's your starting point. And then B is between 0 and 1, so it's going to be a fraction or a decimal, likely, which is your decay factor. And I'm going to put here between 0 and 1. I was going to use the and symbol, but I'm not fond of that. So between 0 and 1 is when it's a decay factor. So again, take a second, write this stuff down, draw the model, and we'll talk about identifying whether there is growth or decay. All right, so here we're going to identify the initial amount, A, and the growth factor, B, in each of these. So in this case, the initial amount would be, or A, would be 14, while B would be 2. So this is definitely growth. For the next one, A would be 150. This is your initial amount. This is also your y-intercept. So this would be 0, 150 on the graph. Just like over here, this would be 0, 14 on our graph. So B would equal 1.0894. Now I want to talk about this. This is like 108.94%. So we would take this decimal and move it this way. So this would be an increase of 8.94%. So here we took 1, this is like 1 plus 1. So this would actually be an increase of 100% because it would be 1 plus 1. Here, our A value is this 25,600. So B is 1.01. So this would be a 1% increase. Because we take that decimal, we move it here. This value is your 1%. Now here, our initial value is 0. So we're starting with nothing. I'm not sure how anything is possible here. But it says 1.4 would be the B. So this would be, and I use these values, this would be a 40% increase. And again, these are all growth. So here we can use this situation to help us write an equation. So it says the number of students enrolled at a college is 15,000. So that's going to be our initial value. The percent of rate of change is 4%, so it's a growth factor. So it would be 1 plus 0.04. So this would be 1.04 as the change. To find the number of students enrolled after 1 year, you calculate 15,000 times 1.04. So this is after 1 year. So what we would do here is we continue the process. So to write our equation, we would write 15,000 as our initial value times 1.04 to the x. So in order to find after 25 years, we would substitute 25 for x to see what our enrollment would be. So I ended up with 39,987.5. Now you can't have half a person, of course, So you can't increase it either because that would mean you're including another person. So then this would be, I would say, somewhere around there. So this would be a good approximation. All right, here's a good one. This is the initial population of 20 rabbits triples every half year. The function given here gives the population after X half year periods. So it says how many rabbits would there be after 6 years? So what we need to do is multiply, first of all, 3 times 2 because this is half years. Whoops. And so we have to double it for each half. So in this case, it would be 6. So we would substitute. So we would do f of 6 equals 20 times 3 to the 6th power. So 20 times 3 to the 6th power. 14,580 rabbits. So this is showing that the number of rabbits is tripling every half year. Now obviously you can draw a table or something if you're more confident with that, but there you go. And that solidifies the phrase, they multiply like rabbits. All right, now let's look at identifying the initial values when we have decay going on. So in this case, it's still A is 5. Now B, the value is 0.5, but remember, this has been subtracted from 1. So what we're going to do is take that value and basically discover what the difference would be between 1 and 0.5. So it's still also 0.5. So this would be a 50% decrease because this is the new value. So let's look at the next one. A is 10 is initial value. We have 0.1 for B. Sorry, I'm moving over here. I'm going to move that decimal. Actually, hold on. I need to decide what's left. So it'd be 1 minus 0.1, which would actually be 90. So that's the original amount. So in this case, it would be a 90% decrease. For the next one, I guess I can switch colors. For the next one, we have 2/3. Actually, let me go back. We have 100 for A, and B is 2/3. So that means 2/3 is the amount we're searching for. So that means 1/3 was taken away. So that means it's a 1/3, I guess, percent decrease. Or a third of something. I don't want to say percent, so it's a 1/3 decrease because I don't know if it's dealing with what item we're dealing with, so it could not be a percent. Initial value 0.1. B is 0.9. So 9 is what we're looking for. That's what's left. So we're actually at 0.1. So when I move my decimal, this would be if it is percent, this would be a 10%. Decrease. I think the decay factors are a little more tricky, but this is a good example of a decay factor. It says the initial value of the car is $30,000, I guess it should be dollars, and it loses 20% of its value with each year. I guess I should have added the rest. It's how much is the value of the car after X years. So our initial value, so A would be 30,000. Now B, this is what we have to do. Essentially what we're going to do is take 100% and subtract the 20% to see what it's worth after the 20%. So it would be 80% or 0.8 in our equation. So 30,000, so it would be y equals 30,000 times 0.8 to the x power. So this will tell us the cost or what the car is worth after X years.